It is July 16, 1945. The New Mexico desert is still dark, wrapped in the cool embrace of the pre-dawn hours. This quiet moment is about to be shattered forever. Scientists and military personnel, hidden in bunkers miles away, hold their breath. This is the Trinity test, the world's very first detonation of an atomic bomb. Suddenly, a light brighter than 1,000 suns erupts from the desert floor. A silent, searing flash paints the landscape in stark, brilliant white. The cameras tasked with capturing this historic, terrifying event are whirring away, but their view is limited. They see the world only in shades of gray, capturing the raw power, but none of the hidden hues of this new fire. The films from that day, and from many subsequent tests in the following years, are iconic. We've seen them countless times in documentaries and history books. A monstrous mushroom cloud billows upwards, a churning, roiling mass of energy. The shockwave ripples outwards, kicking up dust and sand in a ghostly circle. These images are powerful, a stark and haunting record of humanity unlocking one of the universe's most formidable secrets. But they are incomplete. The monochromatic film, while a marvel of its time, could not capture the intricate and terrifyingly beautiful tapestry of colors that physicists knew must be present within the fireball, colors that held the key to understanding the forces at play. These early recordings were a paradox of information. On one hand, they were the most detailed visual data ever collected on such an event. They allowed scientists to measure the speed of the explosion's growth and the scale of the mushroom cloud with incredible precision. On the other hand, the absence of color was a significant scientific blind spot. The incredible temperatures and pressures inside the atomic fireball were generating a whole spectrum of light, from deep reds to intense blues and violets. Each color corresponded to a different physical process, a different temperature, a different state of matter. To truly understand the bomb, they needed to see its colors. So, while the public saw only black and white, a small group of specialists knew there was a hidden story waiting to be told. The challenge was immense. How do you see something that happens too fast for the available technology to record? The answer would not come from a better camera, at least not at first. It would come from a unique and unexpected collaboration. It would require a blend of hard data, theoretical physics, and the patient hand of an artist. The mission was to go back to those grayscale frames and paint the atomic fire, not with imagination, but with the colors of science. To understand why these crucial films were black and white, we have to think about the nature of an atomic explosion. It is an event of almost unimaginable speed. The initial fireball of a nuclear bomb expands from a few meters to hundreds of meters across in mere fractions of a second. To capture this, you don't just need a camera, you need a time microscope. Scientists developed incredibly specialized high-speed cameras machines that could capture thousands or even tens of thousands of frames per second. This was the only way to slow down the blast on film and analyze its growth moment by moment. These incredible cameras came with a trade-off. Color film, especially in the 1940s and 1950s, was a much more complex and sensitive medium than its black and white counterpart. Color film works by layering different emulsions, each sensitive to a different primary color of light, red, green, and blue. This complexity made it slower, meaning it required more light and a longer exposure time to create a proper image. For a high-speed camera shooting at thousands of frames per second, the exposure time for each individual frame is infinitesimally small. There simply wasn't enough time for the light to properly register on the slower color film emulsions. The priority for the scientists at the Los Alamos laboratory was data. Clear, sharp, and sequential data. Black and white film was perfect for this. It was highly sensitive to light, making it ideal for the ultra-short exposures of high-speed photography. It could produce a crisp, high-contrast image that allowed for precise measurements of the fireball's size and the shockwave's progression. Capturing the exact shape of the explosion frame by frame was far more important for their calculations than capturing a blurry, undefined smear of color. They chose sharpness and speed over hue, sacrificing the rainbow for raw information. This decision left them with a mountain of grayscale film and a deep scientific curiosity. The physicists knew the temperatures inside the fireball reached millions of degrees, and basic physics dictates that objects at different temperatures emit light at different characteristic wavelengths or colors. A cooler part of the explosion might glow red, while a hotter region would shine blue or even into the ultraviolet spectrum. The black and white film captured all of this light as a single value, a shade of gray. The challenge became a matter of translation, how to convert that grayscale data back into the scientific colors they knew were there. With reels of high-speed black and white film in hand, the scientists at Los Alamos embarked on a remarkable project. They couldn't retake the photos in color, so they decided to add the color themselves. This wasn't an artistic guess. It was a meticulous, data-driven process. It was a collaboration between physicists, who understood the theories behind the explosion, and technical artists and draftsmen, who had the skill to painstakingly apply color to individual film frames. Each frame became a canvas, and the palette was derived from complex calculations about the physics of the blast. The process began with data. Scientists used instruments called radiometers and spectrometers to measure the intensity and types of radiation emitted by the explosion at different moments. This gave them hard numbers about the temperature and energy distribution within the fireball. For example, they could calculate that at 15 milliseconds after detonation, a specific ring of the fireball would have a temperature of several thousand degrees Celsius. According to the principles of thermal radiation, an object at that temperature would glow with a specific color, perhaps a brilliant orange red. This scientific data was the paint-by-numbers key for the artists. The team then projected the black and white film, frame by gigantic frame, onto a large surface. Guided by the physicists' charts and graphs, the artists would carefully hand-paint color onto each frame. They used special transparent dyes, known as celluloid paint, that would adhere to the film. A specific shade of yellow might be used to represent a particular temperature zone. A deep, angry red could trace the leading edge of the expanding shockwave, showing where the air was being superheated and compressed. Other colors could represent the distribution and intensity of different radioactive elements created in the blast, information completely invisible to a standard camera. This was an incredibly laborious task. A few seconds of an explosion captured at high speed could consist of thousands of individual frames. Each one had to be colored by hand, following the precise scientific instructions. The result was a film that was both a piece of art and a sophisticated scientific visualization. It transformed the flat, grayscale footage into a dynamic, color-coded map of the bomb's physics. What was once a simple recording of size and shape became a visual representation of temperature gradients, pressure waves, and energy release, allowing scientists to see the invisible forces at work. For decades, these hand-colored films were primarily internal scientific tools. They helped researchers at Los Alamos and other facilities refine their understanding of nuclear physics. By comparing the colored films to their computer models, they could see where their theories were correct and where they needed improvement. The colors made it intuitively easier to track the flow of energy and the complex interactions within the fireball. This visual data was invaluable for improving the safety and design of nuclear weapons during the Cold War, allowing for more predictable and controlled outcomes based on the lessons learned from these painted histories. However, as time went on, many of these unique films were classified, locked away in archives, or simply began to degrade. The original celluloid was fragile, and the hand-painted dyes were susceptible to fading and discoloration over the decades. The story of this incredible intersection of art and science was at risk of being lost. It wasn't until the 21st century that a concerted effort began to find, restore, and declassify these films. Film archivists and physicists, like Greg Spriggs at Lawrence Livermore National Laboratory, spearheaded projects to track down the forgotten reels from tests with names like Castle Bravo and Operation Teapot. The restoration process is as meticulous as the original coloring. Technicians carefully scan each frame at high resolution, digitizing the fragile film before it deteriorates completely. Using digital tools, they can correct for color fading, clean up dust and scratches, and stabilize the footage. This work brings the colors back to their original scientific intent, restoring the vibrancy and, more importantly, the information that the original team worked so hard to create. By preserving these films, we are preserving a unique form of scientific data that can still be studied today. Today, these restored and declassified films serve a dual purpose. For scientists, they remain a valuable record of real-world nuclear effects, a benchmark against which modern computer simulations can still be tested. For the public, they are a powerful and sobering window into our history. Seeing the atomic blast in scientifically accurate color, rather than abstract black and white, makes the event more real and visceral. It transforms the mushroom cloud from a historical symbol into a terrifying physical phenomenon, reminding us of the immense power we unlocked and the profound responsibility that comes with it.